Okay, so we saw a few properties of congruences. Just to recall, we saw
Mhm.
that if this property we saw that if a1 b1 is a1 is congruent to b1 modulo m, and a2 is congruent to b2 mod m, then we can add and subtract. They will be congruent, and also the product will be congruent. A1 b1, sorry, a1 a2 is congruent to b1 b2 mod m, right?
Yeah. Additional multiplication.
Right. Addition, subtraction, and multiplication. So, but
Mhm.
one thing also we observed that we cannot divide. So, for example, if it's given that AC is congruent to BC mod m, so it need not be true that A is congruent to B mod m. So, we cannot
Mhm.
just cancel the C from both sides. So, that we
Mhm.
saw an example. But on the other hand, if uh, if we have some extra condition or extra information about C, if C and M are co-prime, that is the GCD is 1, then we can actually cancel the C from both sides and claim that A is congruent to B mod m. Okay,
Right.
right. Okay, so next what you have is, so we can solve equation of for congruences. So in a similar way that of equations. So congruences with unknowns can be solved in the same way that equations are solved. So for example, suppose we have this congruence: x plus 12 is congruent to 5 mod 8. So this is an equation, right? And we have an unknown variable x. Suppose we want to solve for x, right? So then we can
Mhm.
just do what we do in the case of equation. So we subtract 12 from both sides and minus 7 mod 8.
Mhm.
So this gives us the solution, right? So
Okay.
yes. So generally what will happen is, or what we will try to do is, we will try to convert this negative into positive always, right? So what is the equivalent of minus 7 in positive thing? So the thing is, what we learned, if you remember, so any integer is 7. uh, any integer is equivalent to one of these things, right? 0 1 2 up to 7 in module 8. That is one theorem we learned, right, in the beginning,
Mhm.
right? So what will be the corresponding to minus 7?
Uh, Maybe from -1, -1, -2.
No,
So you're saying mod 8, right?
right.
But in the negative side. Okay.
Yes.
So when you divide, let's say, a number mod 8,
Right.
so it could go from 0 to 7, right? Okay. But if you
Yes, yes, the
divide
remainder is always
minus 7, so how would that be?
yes. So to change to positive, what you can do is that we know that 8 modulo 8. So this is 0, right? Because in
Mm-hmm.
modulo 8, 8 is 0, right?
Right.
Right. So what we can do is here we can add 8 on both sides, right? So that will not change the thing because adding 8 is equivalent to adding 0 on both sides in modulo 8, right?
Right.
right? So x is congruent to 1 mod 8. So minus 7 is actually equivalent to 1 mod 8.
Okay.
Okay. So whenever we try to find the solution for an unknown variable, so we'll generally the tradition is to give the solution in a positive term. So if the modulo is n, so we'll try to give the solution from 0, 1 to up to n minus 1. Okay.
So sorry, what's the solution for that?
Which one?
The very last one. 1 mod 8. 1 mod
Yeah.
8 would be 1, right?
No, 1 mod it is not 1, right? So x is, you have to, this is the solution. X is 1 mod 8 because 1 mod 8 is a class, right? It is not a single integer, right? Any number of the form 8k plus 1 is 1 mod 8, right? It's like 1, 9, then 17. It can be anything, right?
Okay, that's
That
the
is a,
solution.
yes, that is a class of numbers because we are modulo 8, right? We are in modulo 8.
Okay, so x could be 1, 9,
17,
17.
right? Anything it can happen.
Okay, that would be x. So when you say 0, 1, 7, 0, 1 to 7, what is that?
Yes, so so these are the possible remainders, right? In modulo 8. So this is the
The
class of
possible
remainders, right?
reminders
Yes.
with model 8, right?
Right.
But if
So
you do, but the minus 7 mod 8, you're
hmm.
saying is the same as saying x equal x equal 1 mod 8.
Yes, it's minus 7. So negative 7 mod 8 is equivalent to 1 mod 8. So this is the set of remainders, but individually this is also a class of if I see the whole integers. So 0 represent to all the things that is a multiple of it, right? So it will come from minus 8, 0, 8, 16, everything will come, right? From negative sign to this thing. Everything is nothing but 0 mod 8, right? Similarly, 1 mod 8, it is nothing but so 1, minus 7, then 1, then your 9, 17, like this, right?
Mm-hmm.
So like this, so individually, so each of the remainder, we can partition the integers into like these classes, right? So this minus 7 is equivalent to 1 in modulo 8.
Minus 7 is 1, okay.
Right?
Because the class you're saying x would be the same.
Right.
Okay, okay.
Right. So this is an example how we solve for, suppose we are given an equation. So how do we solve for the unknown thing? So let us see another example. So suppose you have another equation. So 4x is congruent to 3 mod 19. So here we have to solve for x, right? But the thing is, so 4 and 3. So here we still don't know how to use division, right? We only know multiplication and addition, right? Multiplication,
Yes.
subtraction, and addition. Those three things we know. So what I can do is, so one thing what we know is, so since this is an equation, we can multiply both sides by the same quantity. So
Mm-hmm.
multiply both sides.
This is only for integers, right? No, doesn't work with.
So here the only thing we are working in integers only, everything, because modulo things everything is in integer,
Okay.
right? So we multiply both sides by 5, then what happens? So it becomes 20x is congruent to 15 modulo 19, right?
Mm-hmm.
But one observation is 20. So this I can write as 19x plus x, right?
Right.
But 19x is 0 mod 19, right? Because it is divisible by, right? So
90,
19x
90x is
0 mod 19, right?
0 mod 9.
19 because it is divisible by 19, right?
Okay. Yeah.
Right. So this will go to 0. So x is congruent to 15 mod 19.
So you just remove everything that is zero mod
Yes, yes.
anything.
Yes, 0 mod. So whatever, suppose modulo n we are working. So anything which is 0 mod n, we can remove that because yes.
Mm-hmm.
Right. So the solution is get is x is congruent to 15 mod 19. Right?
Okay, okay. So, yeah.
Right. So here actually we used a particular trick to solve it. So the thing is, so since we don't know division till now, so how to remove this 4? Because I want to find the solution for x, right? So we multiply it by a number such that it is closest to 19, right? So so if I multiply by 5, it is 20, which is closest to 19. Because 20 I can write as 19 plus 1. So that's why I multiplied by 5.
Mm-hmm.
Right. So next what you have is, so to solve a congruence modulo m, we can just try. So each value 0, 1 up to m minus 1, right? For each variable. So suppose we don't have an idea how to solve it, right? So I know that the solution will lie between 0, 1 up to m minus 1 only, right?
Right.
Right. So we can try putting in. So suppose, for example, in this problem, I don't know how to do the solution, right? So, but I know that solution of x will lie within. So x must belongs to 0, 1, 2 up to 18. So within this one,
Yeah, one of them will
plug
be
in
the
each value of
solution.
x. Right. So we plug in each value of x and check whether it is working. So if I put 0, it is not working. If I put 1, it is not working. Like that, we check. So yes. So that is
Mm-hmm.
a brute force type of thing. But yes, sometimes it works because if we don't have an idea how to solve it, we can use that. So let us see an example. So suppose we have x square plus 2x minus 1 is congruent to 0 mod 7, right? So
Mm-hmm.
how to solve it, right? So we know that x must belongs to 0, 1 up to 6, right?
Right.
So yes, can you try which which values of x will work? Can you put in and check? So 0 will not work, right? What about 1?
7,
Yes, tell.
1. Yes, 1 gives you, it works, right? Because 7
1
mod
will be
7 is 0.
so if I put x equals to 1, then what happens? So
Oh,
1 plus,
oh yeah, yeah. 3,
so
2,
it is 2, right? So it is not
2.
congruent to 0.
Okay, okay.
So 1 also does
But
not work.
with 2,
Yes, yes. So that is not 0 mod 7, right? So that will not work.
with x equal 2.
Yes, tell.
Yeah, with x equal 2,
Yes, x equals to 2,
everything is
what
7.
happens?
Everything is 7, and 7 mod 7 is 0.
Right. So x equals to 2 is 2 square plus 4 minus 1, that is 7. And that is congruent to 0 mod m. So yes. So 7, 2 works. What else? So 2 works. What about 3?
No, 3 will not work. I think none of them will work. Everything else doesn't work.
So 3 is 3 square.
9, 15, 14. Yeah, it also works, right?
Right. So this is 0 mod 7.
14,
Right. What
right.
about 4?
Correct. 4 would be 16 plus 8, 24, 23. 23 doesn't work.
Right. 5.
5, 25, 35, 34. No, it doesn't work either.
6.
36,
Plus 12.
48, 47 doesn't work either.
Right. So the only solution are so x is congruent to 2 mod 7 and x is congruent to 3 mod 7. So these are the only solutions, right?
So the solution is
There are two
equal
solutions.
2 mod 7 and 3 mod 7. Okay.
Right. Right.
I see. I see. Okay. Okay.
So for example, yes. So now let us try another one. So if I take the congruence, x square is congruent to 3 mod 10, right? So let us see whether it is working or not. So yes, same idea. So try to put in values. So 0, 1 up to 9. So 0 will not work, 1 will not work. 2 is 2 square 4, that will also not work. 3 square is 9, right?
Mm-hmm.
So that will also not work. What about 4? If I put x equals to 4.
4, 16. No. 16.
Yes. Then
But 16 mod 10 is 6.
right. So that will not work because we want 3.
Okay. 4, 5, 25, 15. 6, 36, 26. I mean, none of them will work. 6,
Yes.
7,
So here will
40,
yes. So the
49.
thing is here. So yes, one thing I think you are doing wrong. So the thing is, when you put 6, then you have 36, right? But 36 is 26. That is fine. But actually it is 6 mod 10, right? Because you have to bring it to
Oh,
the
yeah.
lowest form, right?
Okay, the reminder is 6.
Yes.
Okay.
So remainder is 6. Yes.
7,
So
49, reminder
yes,
is
49
9.
is 9. And
8,
8 square is 64. 64 is 4 mod 10. And
the
9 square
reminder
is
is 4.
81. So 81 is 1 mod 10, right? So here
1
none of them
mod
work,
10.
right? So the thing is, so this congruent does not have any solution. Right.
Okay.
So there
Okay.
can be also congruences, so which does not have solution. So this is an example, right? So because
Yeah.
we know that in our usual equations also there are some equation that does not have any solution, right? So for example, if I take x square plus 1 equals to 0, so that does not have any solution in real numbers, right?
Mm-hmm.
So no real solution. So similarly here, so this equation does not have solution in this modulo 10.
Mm-hmm.
Okay. So now, so we'll next part of the chapter, what we'll do is we'll try to solve this type of congruence. So ax is congruent to c mod m. Okay.
Okay.
Right. So for an example, let us take this one. So 6x is congruent to 15 modulo 514, right? So here for this you have to check whether solution exists or not. Okay.
Okay.
So the thing is, but this if I want to plug in every value and check, that will be huge, right? Because up to 513 you have to check, so that will be difficult, right?
Right.
That is not possible.
Mm-hmm.
So the thing is, can we say something else? Means from any other thing, can we have some observation, right? So
Mm-hmm.
so this implies that 514 divides 6x minus 15, right?
Mm-hmm.
So this is fine, right, by definition.
Yes, yes. So yes, according to currency.
Yes. So now, but what I have is this 6x is an even number, right?
Yeah, it must be even minus odd would
Well,
be even, right?
no, no, odd, right?
But 514 is an even number.
Right. So that's why this does not have any solution. So 6x minus 15 is always an odd number.
Okay, so even minus odd is odd.
All right.
So
So
it's odd.
this cannot be divisible by a even number. So which is even. So hence this does not have any solution.
Right.
Right.
Hmm. Yeah.
Right. So let us try to see any other another few examples to get an idea. So suppose the next example is, so 18x is congruent to 8 mod 22, right?
Okay.
So now if you remember, so this is nothing but 2 times 9x is congruent to 2 times 4 mod 22, right? But the thing is we cannot cancel 2, right? So these
Uh-huh.
2 and these 2 we cannot cancel because GCD with 22 is not 1, right?
Mm-hmm.
So this thing will not work. So yes, any other thing we have to do something else. So what I know is that from this thing that 22 divides 18x minus 8, right?
Mm-hmm. Yeah.
So this implies that
18x
18x,
minus 8 is equal to 22k.
right? So 22k for some k,
Now
right?
you can simplify there, right?
Yes, yes. So from here we can simplify for some k, right?
9 for 11k.
Right. So what you can do is okay.
Mm-hmm.
So from here what you have is 9x minus 11k equals to 4. Okay.
Right.
So we have to find integers x and k such that 9x minus 11k equals to 4, right? But we have an idea, right? So because so GCD of 9 and 11 is 1, right?
Mm-hmm.
So since GCD is 1, so we can apply the equivalent algorithm to get an idea, right? So
Okay.
so if we equivalent algorithm we can apply. So 11 equals to 9 plus 2, right? Then 9 equals to,
Sorry. Oh, okay. You are trying to find okay, you're doing the reminder, right?
yes, yes. So the thing is the GCD of 9 and 11 is 1. So equivalent algorithm I want to find some 9u plus 11v equals to 1.
Nine you right. Okay. Okay, so 9 would be equal to 4 multiply 2 plus 1,
Right. So we
and
can now
then
backtrack. So 9 minus 4 into 2. So 9 minus 4 times 11 minus 9. So it is 5 times 9 minus 4 times 11. Right?
yeah, 5 times 9 minus 4. Yep.
Right. So what I can do is, so this I know this is equals to 1, right? So now if I multiply, so multiply by 4 on both sides.
Right.
So then what I have is 9 times
20 minus 11, 16 times
4, right?
equal 4.
So
Right.
this is of this form, right? So
Yeah,
I
it's
can take
of
this
that
is
form.
right. So I can take excess. So from here I know that x is of the form 20 modulo 22, right?
Yeah.
So that is the solution. So this way also we can find a solution.
Okay, so you try to find the GCD, and that also helps to
Right.
find a solution. Okay.
Right. So next what we have is okay. So one more solution actually works for this case. So we have 18 equals to 8 mod 22, right? So x equals to 20 works, but if I put x is 9, then check once, is it working? So 18 into 9 is how much?
Sorry.
18 into 9.
18 to 9.
Right. 18 times 9.
Where are you? Sorry, where are you trying to do that?
Yes. So I want to see. So I want to show you that another solution is there. So that is not coming from this part. So what we did till now, we are getting only one solution to the equation, right?
Mm-hmm.
Yes. So if you do 18 times 9, how much is coming?
18 times 9.
Yes.
Let's see. It's 162
Right. Minus 8.
minus say 140, 154.
Yes. So that is divisible by 22, right?
Yep.
Right. So 9 is also a solution, but that solution is not coming. So x equals to 9 mod 22. Right. So it is also a solution,
Mm-hmm.
right?
Yep.
So we'll let us see how to bring this solution, because if we want to solve a equation, we must find all the solutions, right?
So we did the GCD, and then we found that x equal to 20 and k equal to 16, but we don't care about the k. We only care about the x.
Right.
X is equal to 20. Okay. But then you are saying that if we just try 9, it's
Yes.
also a solution of 18x equal 8.
Right. But this solution we are not getting by the above method. What we did, right?
Right. So, okay.
Okay. So that will come later. How to bring this solution also. Okay. So this is some examples. So the main congruence or general congruence that we are trying to find out is, so ax is congruent to c mod m, right? Where a and c are integers. We want to solve this, right? Integer solution to this thing. So
Mm-hmm.
so from here I know that m divides ax minus c. So from here we can write that ax minus c equals to some my for
Okay.
some integer y.
Mm-hmm.
So so what we have is so this has a solution if and only if the linear equation ax minus my equals to c has a solution, right? So this is a general observation.
If only the linear equation has a solution. Ax minus ay equal to c. Right, has a solution. Has at least a solution because there could be many solutions.
Yes, yes. So the thing is, I can say that this congruence, linear congruence, that has a solution if and only if this equation has a solution, right?
Mm-hmm.
Right. So, so to prove it, or not proving, but just to make it clear. So suppose G is the GCD of A and M, right?
Mm-hmm.
So then this AX minus MY. So this is always a multiple of G, right?
Mm-hmm.
Right? Because G, if G is the GCD of A and M, then G divides AX minus MY, right?
So the GCD of A and M. So
Yes.
um, so wait, so AX minus MY, you're saying is always a multiple of the GCD of A and M?
Right, right. That is true, right?
I mean, how come?
Yes, that is what I'm saying. So, so from here, what I have, G divides A and G divides M, right? Because this is the GCD, right?
Mm-hmm.
So, so A equals to some GK1 and M equals to GK2, right?
Mm-hmm.
So AX minus MY, you can rewrite it, right? Using this thing. So G I can take common. So K1X minus K2Y. So G also divides this one, right? AX minus MY. And hence it is a, hence this quantity is also is always a multiple of G, right?
Mm-hmm.
So now it's fine,
Let's see.
right?
1 second, 1 second. So you're saying, okay, okay,
Right.
all
So the
right.
thing is, yes. So that's why. So this may not always have a solution because if C is not a multiple of G, then this equation does not have a solution, right?
Right.
So that is the observation. So if G does not divide C, then Ax minus My equals to C has no solution, right? This
Mm-hmm.
implies that the original congruence also does not have any solution. So Ax congruent to C mod M also has no solution. Fine.
If G does not divide C, so that's another. You're saying another characteristic.
Right, right. So if the GCD of A and M, so that is the G, right? So if the GCD of A and M does not divide C, then this equation, this linear equation AX minus MY equals to C does not have a solution, which will in turn imply that the original congruence also does not have any solution.
Because in congruence, what we do is we divide AX, we divide it by N.
Right.
We divide it by N, right? And then we try to find if the remainder of that division is equal to C, right?
Right.
So
in
you're
other
saying
words,
G.
in other words, if I subtract the C from AX, so it must be divisible by M, right?
Sorry.
Yes. So remainder, we want to find whether the remainder is C or not, right? So if the remainder is C, that is same as saying that if I subtract the remainder, it must be divisible, right, by M.
If the remainder is M, what else?
No, remainder is C.
Okay, if the remainder is C.
Right. Then if I subtract it, so it must be divisible by M, right? So M must divide this AX minus C.
Yeah, that of course, that
Yes.
also works. But G is the GCD of A and M, and you're saying if the GCD of A and M is not a divisor of C, then of course,
Yes.
yeah, that I think I understand.
Right. Because these two things are equivalent, right? So this condition, this has a solution, is even only if this linear equation has a solution, right? So if I can show that this does not have a solution, this implies that this will also does not have any solution. So that's why we are finding this condition, that if I take G to be the GCD, if G does not divide C, then this does not have any solution. So which implies that the original congruence also does not have any solution. Okay. Okay. So the next part is so now we assume that suppose G divides C. So then what happens?
We suppose what?
G divides C. So we saw that if G does not divide C, then what happens? We saw. So next we assume that G divides C. Then how to give a solution? So if G divides C, then so G is the GCD of A and M, right? So this implies by Euclidean algorithm, I have AU plus MV equals to G, right? For some U and V, right? That is by Euclidean algorithm, right? So now, so see, so suppose we find a solution. Find a solution. Suppose U equals to U naught and V equals to you can say U0 and V0, right? By Euclidean algorithm, right? And we know that G divides C, so we can multiply the whole equation by C by G, right? So since G divides C, so C by G is an integer, right? So if I multiply, so AU naught times C by G plus MV naught times C by G equals to G times C by G. So we multiply the whole equation by C by G.
Okay.
So from here,
C over G is an integer because G is a divisor of C, right?
no,
Okay.
the other way around. G divides C.
Okay.
So this equals to C, right?
Mm-hmm.
So when I take modulo, then what I have is, so A this is congruent to C mod M, right? Because when I
Right.
take modulo M, then this part will go to 0 because I have a multiple of M, right? So this is our X. So X is congruent to, this is the solution,
Mm-hmm.
U0 times C by G modulo M. So this is our solution to the linear congruence, right?
Mm-hmm.
So now the condition is, so this will give you one solution, right? So that we already saw in the previous example. But how to find that whether there are other solutions or not, right? So the next question is, so are there other solutions, right?
Okay.
So suppose this is our first solution. So we denote it by x0. So suppose that x1 is some other solution to this ax congruence to C mod M. Then we must have that ax1 is also C mod M, right? Because x1 is a solution, and we already know that ax0 is also C mod M, right? Fine.
Let's see. X is a model solution to so AX1.
Right.
Mm-hmm. Mm-hmm.
This is fine.
What's the console?
No, what I'm saying is, so one solution is x0 that you already found out. So suppose we are telling that there is one more solution, right? So suppose we want to find other solutions also. So suppose x1 is a different solution than x0, right?
Mm-hmm.
So since x1 is a solution, x1 also will satisfy this congruence, right? So that's why ax1 is C mod M. Fine?
Mm-hmm. Yeah.
Right. So from here, combining these two, what we can say is, so ax1 is congruent to ax0, right? Mod M,
And they are congruent, yeah.
right? They are individually congruent. So what I have is that M must divide their difference, right?
Mm-hmm.
So since G is the GCD, so M by G must also divide A of this 0 by G, right? Because A and M has
Okay.
GCD G, right?
Right.
So right. So now so GCD of A and M is G. So this implies, so GCD of A by G and M by G. So this is 1, right?
Oh, yeah.
Okay. So this we can write as right. So since GCD is 1, so from here we can conclude that m by g must divide x1 minus x0.
So m by g must divide.
So m by g is dividing the product of these things, right? But I know
Right.
that these two are co-prime, so it has to divide the other part only, right?
So you're just removing a and g because you proved that the division is one from both.
Yes, yes. So they are GCD is 1, so this part must divide the other part only. This cannot uh, have a factor inside a by g.
Okay, okay.
Right. So from here, what I have is, so this is equals to some k times m by g. So what I have is x1 is equals to x0 plus some k times of m by g, right?
Mm-hmm.
Okay.
Mm-hmm. Yeah.
So what we can do is we can vary our k and find different mode solutions. But k can be only k must belong to 0, 1 up to g minus 1, because
Oh,
after
g minus one.
yes, because after that it becomes same in modulo m, right? So that is the thing. So this is the complete set of solution to our whole things.
So x1 equals to x0 plus k n divided by g, and g is the GCD of a and m.
Right.
Okay,
So
okay.
yes, so now we will go back to our previous thing and check how to find that we found one solution, right? So here, here we found one solution. So now using the formula we obtained, we will find this solution also. So let us do that. So 20 we found, right? And our original congruence was 18x equals to 8 not 22. So right,
Mm-hmm.
the GCD is how much? So GCD of 18 and 22 is 2, right?
The GCD is 2, right?
Right. So this is our G, this is our M, right? And X naught, the first solution we got as what was the solution we got? 20, right? Yes.
20.
So X naught is 20. So if I put into this formula, so what I have? So X1 is 20 plus K times M is 22, 22 by 2, right?
N is 22 and G is 2, right?
Right. So yes, so this is reduced to 20 plus K times 11, right? So and K must belong to 0 and 1 only, right?
0 and 1, right?
So 0 gives 20 itself. So the next solution is 1. So 1 is, so if k equals to 1, then x1 equals to 20 plus 11 is 31, right?
Right.
But 31 in modulo 22 is how much? If I do modulo 22, so,
9.
right. So that is the second solution. So this is how we solve it.
0 will not work there because 0
0 will give back the original solution, right? So 20 we
0
got
will give
already.
you the 20 that we have already. Okay.
Yes, yes. So from here we'll get an idea how many solutions will exist, and we can explicitly find all the solutions.
I see. But we need to find one X.
Yes, yes. First we have to find one solution. Then only we can find others. Because one solution is easy to find, right? So one solution we can always find from the Euclidean algorithm, right? So if this condition is satisfied, that GCD, so GCD, if the GCD divides C, then we know that one solution exists, that is using the Euclidean algorithm, right?
Mm-hmm.
Fine.
Yeah.
So next we'll summary everything what we done in a single theorem. So what are all the observations we had? So that is called the linear congruence theorem. So what did you say? So let a comma c and m be integers with m greater than equals to 1, and let g be the GCD of a and m. Then the first point is, if g does not divide c, then the congruence Ax congruent to C mod m has no solution. And the second point is, if G divides C, then the congruence Ax congruent to C mod m has exactly G incongruent solutions. So for example, here G was equals to 2, right? So that's why we got two solutions, right? So it has exactly G incongruent solutions, and also they are telling explicitly. So to find the solutions, first find a solution. Suppose u0 v0 to the linear equation au plus mv equals to g. Then x0 equals to c u0 by g is a solution. To x congruence to c mod m, and the complete set is given by complete set of incongruent solutions.
Incongruent solutions?
So incongruent solutions means they are not congruent to each other, right? So for example, in modulo 22, 9 and 20 are distinct numbers, right?
Okay.
So they are not same, right? So that's why incongruent. Incongruent solutions is given by this whole set. So x0 plus k times m by g. So where k is 0, 1, 2 up to g minus 1. So this give you g, all the g solutions. So this is the whole summary what we learned till now. So this everything we proved, right? So first part we also proved, second part also we proved.
Right.
Fine. Okay. So maybe today we'll stop here now.